Welcome back. In this lecture, I will continue my discussion on thermal properties, and in today's lecture I will cover crystalline state of polymers. Before I start on crystalline state, let me complete a couple of discussion on glass transition temperature from last lecture. In this slide, I will discuss about the glass transition temperature for copolymers. If I have two monomers which are getting incorporated in a polymer forming a random copolymer as shown here, then the Tg of the copolymer, random copolymer, can be expressed in various equations. One of such equations is shown here, where Tg of the copolymer is given by this expression, where W A and W B are the weight fraction of A and B in the copolymer. Tg A is the homopolymer's Tg. In this case, if this is A, then the Tg A is the glass transition temperature for this homopolymer, and Tg B is the glass transition temperature for the other homopolymer. This equation generally overestimate the Tg of the copolymer. Hence, there is another equation proposed by Fox, and the equation is given by this expression, where again W A and W B are the weight fraction of A and B respectively in the copolymer, and Tg A and Tg B are the homopolymer Tgs. Remember, in this case we need to express the temperature always in Kelvin, not in centigrade or Fahrenheit. It has to be always expressed in Kelvin. Now, this is about random copolymer. If I have a block copolymer, then what will be the Tg of the block copolymer? Now, this Tg depend on the miscibility behavior of the two blocks as shown here. If the two blocks are miscible, completely miscible with each other, then the resulting Tg will be obtained by this expression as well. If they are completely immiscible, then we will have two Tgs, one corresponds to this block and the other corresponds to the other block, which means Tg A and Tg B. There could be a small deviation from the homopolymer Tgs, but it will be very close to those Tgs. So, if we have a miscible, then single Tg given by these expressions, and if it is immiscible or partially miscible, then we will have two Tgs. If we have an alternate copolymer, then obviously it is a 1:1 copolymer by mole. So, from the knowledge of the molar mass of the monomers, we need to find out what would be the weight fraction of corresponding monomers, and we can use this expression to find out the Tg of the copolymer. Similarly, we can also use this expression to find out Tg for polymer blends. Polymer blends are basically a mixture of one or more polymer. In this case, I have shown two mixture of or blends of two homopolymer, this one and this one. In this case, again, if these two polymers are completely miscible with each other, then we have single Tg, and the Tg will be given by this expression, and this is the expression which most frequently used, which is Fox equation, and again remember that T is in K. If this is completely immiscible, then 2 Tgs would be given by Tga and Tgb, and if they are partially miscible, then there will be 2 Tgs, but they are different from Tga and Tgb. So, there will be 2 Tgs, but they will be different than. So, it will be they will be slowly merging with each other. As the miscibility increases, these 2 Tgs actually merge with each other to form a single Tg as the miscibility goes up. Now, I move to today's topic on crystallinity of polymers. Now, in crystal, polymer chains packed together in 3D ordered structure held by intermolecular van der Waals forces like hydrogen bonding interactions. Crystals diffract X-ray at wide angles, and as I have discussed earlier also, that polymers are only semi-crystalline, 100% crystalline polymers are not possible because of the large molecular weight of the polymer, and in general in a polymer melt the polymer chains remains as a entangled mass. And the melting range, unlike the small molecule where melting point is a very sharp melting point, but in case of polymer the melting point is not very sharp, there is a melting range, and that is because of presence of this amorphous regions between the crystalline domains, and those amorphous regions actually affect the Tg of the polymer, Tm of the polymer, and hence this the Tm is generally more broad in nature. And the microstructure, that means the microstructure of polymer sample containing both amorphous and crystalline domain actually determine the material property. And in effect, when we talk about semi-crystalline polymer, we have a non-equilibrium composite microstructures. Remember, we were using the term non-equilibrium because when you form a polymer sample from a melt, then we hardly get a equilibrium structure, because again because of the large molecular weight we do not usually give enough time to reach a thermodynamically more equilibrium state. So, non-equilibrium composite microstructures are formed by coexistence of amorphous and crystalline domains. Semi-crystalline polymers are major polymers in polymer industry. About 70% of the volume, the total global production of all synthetic polymers are semi-crystalline, which means that completely amorphous polymers accounts for about 30% by volume when you talk about synthetic polymer industry. By varying degree of crystallinity and or anisotropy, the properties of the same polymer, same chemical structure, the polymers having same chemical structure can be improved by order of magnitude by changing the microstructure or degree of crystallinity. Crystallinity can be varied by changing processing condition or introducing slight variation in the molecular architecture. For example, barrier properties of PET varies significantly depending on annealing condition. Annealing condition is actually induces crystallinity in the polymer. So, if we change the annealing condition, the extent of crystallinity also changes. As a result, the barrier property of PET significantly changes depending upon the type of or time of annealing we are providing to the sample. Similarly, mechanical strength of a crystalline isotactic polypropylene is 100 times more than a rubbery atactic polypropylene. That is understandable because crystalline domains will give more rigidity in the polymers, hence the mechanical strength goes up tremendously as we increase the crystallinity in the sample. Now, as we know that in say in case of polymer melt, the polymer chains are of different, if I draw a different, they are entangled in like this, and see if I draw 3 different chains, so they will be like this. Now, if we want to make this polymer melt or polymers in solution to crystallize, then the polymer structures has to be regular in the sense they will, when they actually crystallize, they will pack say in a like this. So, unless the structures are regular, then they cannot pack like or pack in a 3D crystal. Hence, this regularity of molecular structure is a must, and also if these polymers interact with each other, like attract each other. So, which means if the intermolecular forces are high between the polymer chains, then also the sample becomes more crystalline or crystallinity becomes easier to induce in the sample. Now, there are other indirect ways also we can introduce crystallinity. Before that, so if we discuss if we compare the crystallinity of a homopolymer and a block copolymer and a random copolymer, obviously because of the structural regularity, homopolymer and block copolymer will crystallize more easily, whereas the random copolymer, it is very difficult to crystallize. Similarly, when you are talking about tacticity, when you have isotactic or a syn diatactic, there is a possibility that this will crystallize, whether atactic polymers generally do not crystalline because of irregularity in their molecular structure. As I was discussing, that there are ways we can induce crystallinity, and first thing that if we give enough time to the polymer chains to rearrange themselves and align with each other to form crystalline domain, then obviously we are giving opportunity to the polymer chains to crystalline. Hence, slow cooling of the molten polymers will induce crystallinity. If we do fast cooling like you do in a injection molding or in a say extrusion machine, it is basically we quench the sample, we bring down the temperature of the polymer samples very quickly. That will hardly induce any crystallinity, because we are not giving enough time to the polymer chains to rearrange themselves and align with each other to form crystalline domains. Similarly, if we evaporate polymer solution, then evaporation is a slow process. As the polymer solution evaporates, the polymer chains come close to each other and they can align themselves, because they are getting more time during evaporation process, and they can actually form crystalline domain. Similarly, annealing is basically heating a polymer sample at a specific temperature between Tg and Tm. So, polymers will have enough mobility because it is above Tg, but it will have tendency to crystallize because it is below Tm. Hence, if we give enough time and if we give enough mobility, then polymers actually, if the crystallability, if the tendency to crystallization is there in the polymer sample, then by annealing we can induce crystallinity. And there is a term crystallization, and there is a corresponding temperature called Tc, crystallization temperature, is also related to this annealing process and or the crystallization process. Similarly, if we stretch a sample above Tg and give enough time, then while stretching, if we stretch, that means we are aligning the polymer chains, and while aligning and we have doing it in above Tg, that means polymers have some mobility, then they can actually now reorient easily and form crystalline domains. So, these are some of the techniques or some of the indirect ways by which we can induce crystallinity in the sample. This is just to show that how crystallinity varies with cooling rate. If we cool or a polymer melt slowly, then the crystallinity will be higher, because again if you are giving more time to polymers to rearrange themselves and align with each other. But if we quench the polymer, for example, as I said in the injection molding or extrusion process, when we cool the polymer melt very fast, then we are not providing enough time, which means the extent of crystallinity is much lower compared to a cooling where it is slower process. So, if we basically slow the cooling process, polymer melt cooling process, we induce more crystallinity in the sample. We will talk about models of crystallinity. There are two main more popular model. One is fringed micelle model for low crystallinity. As you can see that this is a fringed micelle model where we have crystalline domains as well as amorphous domains. These crystalline domains formed by various polymer chains, and also a single polymer chain can contribute to two crystalline domains or more than two crystalline domains. For example, this particular chain is part of this crystalline domain as well as this crystalline domain, and these are kind of micelles what we have learned in our colloids classes, that they form kind of self aggregation. In this case, this is crystalline domain and these are amorphous domains. There is another model for crystallinity is folded chain lamina model, where basically these lamellas are formed, crystalline laminas are formed by arrangement of folded chain. Again, one lamina will contain more than many more polymer chains, and similarly one polymer chain can be part of more than one lamina, and there could be three possible lamella model. One is regular adjacent folds like this, there is irregular adjacent fold, like you have these foldings are irregular as you can see here compared to a regular here, and third one is non adjacent switch back. So, in this case this switching back, like one segment polymer segment is coming and switching back, in this case this switching back is not non adjacent to each other. So, these are the three possible models for folded chain lamella, and as we know from our previous knowledge as well, that crystallinity is embedded within the amorphous matrix. Hence, we call is a semi crystalline sample which is have both Tm for the crystalline domains and Tg for the amorphous domains. Now, if we compare crystalline polymers versus amorphous polymer, we see that crystalline domains, because of presence of crystalline domains, crystalline polymers have higher stiffness, higher density, higher solvent or chemical resistance. Because of the close packing, solvent or the chemicals cannot diffuse in and do the harm to the polymer chains. Because of the presence of crystalline domains, it actually hinders the movement of gases through the polymer chains, hence it has lower permeability or more barrier property. So, that is why semi-crystalline polymers are used in as a container or as a storage of perfume bottles or some applications where you need to have a barrier property to prevent gases from diffuse out from the sample. Similarly, crystalline polymers have higher heat capabilities and very good electrical properties. Not everything is good for crystalline polymers, there are few inferior properties compared to amorphous polymer as well, and the most important is loss of transparency. Because of the crystalline domains present in the sample, they scattered light, and as a result the transparency comes down depending upon the extent of crystallinity. And this is very important because some applications where transparency is a must, in those applications these semi crystalline polymers are not very useful. Because the polymer chains are tied up with each other or they are crystalline, most of the parts or some part, their impact strength actually comes down, because to have a higher impact strength the polymer chains must be flexible enough to absorb the sudden impact or sudden input of mechanical energy and diffuse that, which is not possible for semi crystalline samples. And also because the density is not homogeneous, in the sense that some part is less dense than the crystalline part which are more dense, then it has also anisotropic or differential shrinkage, because it shrink more in one direction compared to the other directions. We will talk about thermodynamics of TM and TG. Now, in thermodynamics we talk about two types of transitions. One is first order, another is second order transitions. In first order transition, Gibbs free energy as a function of any state variables like volume, pressure and temperature is continuous. So, G varies with V, P or T in a continuous manner, there is no discontinuity, but the first partial derivative of G with respect to these variables, they are discontinuous. So, the first derivative is discontinuous. So, we call this a first order transition like melting and vaporization. In fact, these are the proper thermodynamic transitions. The second order transitions are those transitions where these first derivative are not discontinuous, but the second derivatives are discontinuous. For example, glass transition. I will just discuss more quantitatively in the next slide. So, we know from our knowledge of thermodynamics that for a closed system and no irreversible change in composition and phases, we have this expression. So, for a first order transition, if we plot G versus either T, V or P, we will not have a discontinuity. So, this side is, see, if we talk about temperature, now if we just talk about temperature, if we talk about G and this is T, then this side is melt and this side is solid. So, there is this is the melting point, but in this case the transition is not discontinuous. But the first derivatives which are Tg, dP, V or minus S or H. So, if we plot instead of G, if we plot say either V, S or H with say T or other or V or V or V or P, then we get a discontinuity at melting point Tm. So, in this case the first derivative is discontinuous, where the original G is not discontinuous. Similarly, so we call this as a first order transition, but in case of second order transition, these values are not does not change discontinuously at transition, but the second derivatives like alpha or kappa or the heat capacity, they actually changes discontinuously with say temperature or pressure or volume. For example, in this case if we plot V, S or H against T, then this is Tg. In this case this does not vary discontinuously, where if I plot say Cp versus T, then it actually changes discontinuously at Tg. So, Tg is a second order transition, whereas Tm or melting is a first order transition. And in true sense, this melting or vaporization are actually, these are actually thermodynamic transition, true thermodynamic transitions, whereas second order transitions like glass transition, they are not true thermodynamic transition, because the value of this transition temperature depends on the rate of cooling, how fast or how slow we cool the sample. Now, we now look at the factors which influence Tg. Now, we know for a closed system, delta H is given by delta G is given by delta H minus T del S, and M indicates melting process. And so, these delta H M and delta S M represent the enthalpy and entropy of melting or fusion per repeat unit respectively. And at equilibrium, so at melting point at equilibrium temperature, delta G is 0, hence melting point is given by delta H M by delta S M. Now, as the polymer chains are from a molten state, when we cool it and it form a crystalline domain, the polymer chains having a random orientation, much more flexible, they are becoming stiff and oriented arrangement. Then delta S must be negative in this case, and because there are intermolecular attraction between the polymer chains, delta H M also negative in this case, and depending on the magnitude of delta H M and delta S M, T M will vary. So, higher is the value of magnitude of delta H M, higher will be T M, and smaller is the value of delta S m, the higher will be T m, which means that if we have a stiff polymer chain and then we are taking the stiff polymer chain from a molten state to a crystalline state, the amount of entropy loss it will incur will be lower compared to a when you convert a polymer melt having more flexible chains to a crystal domain. So, first case when the polymer chains are more stiff, it will be much more easier to crystallize the polymer chain than a flexible polymer chain, which is understandable. You can also imagine that if we have like small kids, it is very difficult for us to make a line and make them to arrange in a line, but where if you have older people, then it is easier for us to make them a line. Similarly, if the interaction between the intermolecular attraction between polymer chain increases, then it is easier for polymers to become crystalline. So, with this in mind, we will look for the structures, and so there are we will look for the structure, we will determine these values. So, number of factors which dominate the capacity or tendency of the polymers to form crystalline region, and as a general rule only linear polymers can form crystalline. As you can understand, if there is branched polymer, then the arrangement is a difficult thing. So, it is not possible to form crystalline. Stereo regularity, as we discussed earlier, that atactic polymers generally do not crystallize. So, stereo regularity is also very critical. Similarly, copolymer, again I discussed earlier that random copolymer generally do not crystalline, but if you have a regular block type copolymer, then it is possible to crystalline. And again this also I have discussed that slower cooling promotes crystal formation and growth. So, what are the factors that determine Tm? The factors will determine is the backbone stiffness, polarity, backbone symmetry, pendant group regularity, pendant group type and size, absence and presence of branches, and pendant group polarity. And so, basically these all affect either del H m or del S m. As I discussed that if stiffness increases in the polymer chain, then this becomes less negative. So, Tm will go up, that means it is easier for the polymer chains to crystallize. Similarly, the polarity increases, which means there will be more intermolecular attraction. So, magnitude of del H will go up, that also will increase the value of Tm, because it will become more easier for the polymer chains to crystallize. Similarly, symmetry, backbone symmetry will help in crystallization, and if there regular pendant group small size, it will help in crystallinity, and absence of branch will help in crystallinity. Other side, presence of branches will inhibit any crystallization, and pendant group polarity also matters, because if the polarity is higher for pendant groups, then it helps in crystallization. So, to increase Tm or melting point, we should increase the chain stiffness, we should increase the intermolecular attractions, and if we have some groups which can contribute in hydrogen bonding, then it helps in crystallinity, and if we have molecular regularity which helps in packing, then also it helps in crystallinity. So, in next lecture what I will do, I will give example of this factor, how these factors affect crystallinity with some polymer structures.